Good morning students, this is Latif sir. In this video, I will discuss about imperfection in crystalline solid. Imperfection or defects in crystalline solid. So first you have to know what is imperfection or defects in solids. Defects or imperfection in solid are basically irregularities in the arrangement of constituent particles. You know, in solid state the particles are mainly in crystalline solid the particles are properly arranged, they are orderly arranged. But if there is any irregularities in the arrangement of constituent particles, then this irregular arrangement of constituent particle in crystalline solid is known as imperfection or defects. Okay, so first, what is defect? First question, what is defect? The defects are basically irregularities in the arrangement of constituent particles, and defects are two types. One is point defects, another is line defect. First, point defect. Point defect means irregularities in the arrangement of particles. Point means particles. Okay, so point defects are the irregularities or deviation from ideal arrangement around a point or an atom in a crystalline solid. Point defect are the irregularities or deviation from ideal arrangement around a point or an atom in a crystalline solid. Whereas line defect are the irregularities or deviation from the ideal arrangement in entire rows of lattice point, and this is line defect, and in your syllabus only point defect is given. Okay, and these irregularities are called crystal defects or imperfection. Okay, so we shall confine our discussion to point defect only. Okay, this is because only point defect is given in your syllabus. So first question, what is imperfection or defect? It is defects are basically irregularities in the arrangement of constituent particles, and defects are two types: point defects and line defects. Point defect is the irregularities or deviation from ideal arrangement around a point or an atom in a crystalline substance. Okay, and now see types of point defects. Point defects are three types: stoichiometric defects, impurity defect, and non-stoichiometric defect. Point defects are three types: stoichiometric defects, impurity defects, and non-stoichiometric defect. So first, stoichiometric defect. What is stoichiometric defect? These are point defects that do not disturb the stoichiometry of the solid, that is that do not disturb the composition of the solid. Okay, so stoichiometric solids are the point defect stoichiometric defects are the point defects that do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamics defects. And stoichiometric defects are basically two types. One is vacancy defect and another is interstitial defect. These are stoichiometric defect. Stoichiometric defect are two types. One is vacancy defect, another is interstitial defect. So first, see vacancy defect. Vacancy defect, this figure is for vacancy defect. You can see two particles are vacant. Okay, two particles are absent from the crystal lattice. This is vacancy defect. Okay, two particles, one particle from here, another particle from here, they are absent from the crystal lattice. So first you have to see what is vacancy defect. When some of the lattice side, that is lattice point, are vacant. Lattice point means constant particles. the crystal then the crystal is said to have vacancy defect. When some of the lattice sites are vacant, the crystal is said to have vacancy defect, and this result in decrease in density. This result in decrease in density of the substance because some constituent particles are absent from the crystal lattice. And this type of vacancy defect, this defect can also develop when a substance is heated. And second type of stoichiometric defect is interstitial defect. An interstitial defect look like this. Here it is given. This is interstitial defect. Some constituent particles are present in the interstitial empty sites within the crystal lattice. Okay, they displace from their own position. So what is interstitial defect? When some of the constituent particles, that is atoms or molecules, occupy interstitial site. Interstitial means empty spaces, empty void spaces in a crystal lattice. These are called interstitial site. Okay, so when some of the constituent particles, that is atom or molecule, occupy an interstitial site, the crystal is said to have interstitial defect, and this defect increases the density of the substance. And vacancy and interstitial defect are, as explained above, can be shown by non-ionic solids also. An ionic solid must always maintain electrical neutrality. In any ionic solid like NaCl, CuSO4, in any ionic solids, they always maintain the electrical neutrality. Okay. Now see two type of important defects. One is a Schottky defect, another is Frankel defect. These are basically vacancy defect, and interstitial defect found in ionic crystal. Okay, so see what is Frankel defect. Frankel defect is mainly, it is Frankel defect. In this defect, this type of defect is shown by ionic solid. I have already told, there's ionic solids. There's two type of defect. One is Frankel defect, another is Frankel defect, another is Schottky defect. And Frankel defect mainly interstitial defect, and Schottky defect is mainly vacancy defect. So first, Frankel defect. This defect is shown by ionic solids. Frankel defect is shown by ionic solids. Okay. And in this type of defect, Frankel defect, the smaller cation, generally generally cations are smaller than anion. So a smaller cation is delocated from its normal site to an interstitial site. Okay. In Frankel defect, the smaller ion, generally the cation, is delocated from its normal site to an interstitial site, and it creates a vacancy defect at its original site and an interstitial defect at its new location. I am showing you what is Frankel defect. This is the Frankel defect. Actually, this is actually interstitial defect. The cation is displaced from its original site, and see, you can see this is the interstitial site. The cation is present in the interstitial site, but its original position is this one. Okay. So Frankel defect is mainly interstitial defect. In this defect, the smaller cation is delocated from its normal site to an interstitial site, and it creates a vacancy defect at its original site, and and an interstitial defect at its new location. Now see which type of substances show Frankel defect. The substances are zinc sulfide, silver chloride, silver bromide, silver iodide. This type of substances, they show Frankel defect. Okay, Frankel defect also called dislocation defect. It does not change the density of the solid. Frankel defect does not change the density of solid, and Frankel defect is shown by ionic substances in which there is a large difference between the size of ions. There is a large difference between the size of ions. Okay, and Frankel defect, you have to remember that Frankel defect does not change the density of solid. Now say Schottky defect. It is basically vacancy defect. I have already told. It is basically vacancy defect in ionic solid. Okay, and in order to maintain the electrical neutrality, the number of missing cations and anions are equal. That is, in Schottky defect, equal number of cations and anions are missing from the crystal lattice. In Schottky defect, equal number of cation, you can see one cation is missing from this side and one anion also missing from this side. Okay, from this side one anion is missing, from this side one cation is missing. So equal number of cation and anion are missing from the crystal lattice in Schottky defect. And this is vacancy defect because equal number of cation and anion are missing from the crystal lattice. Okay, and Schottky defect also decreases the density of the substance. This is because the cation and anion are missing from the crystal lattice, thereby the density of crystal decreases. So Schottky defect also decreases the density of substance. Okay, and which type of substances so this type of Schottky defect? Examples are sodium chloride, potassium chloride, cesium chloride, silver bromide. Silver bromide, this substance can show both type of defect, that is Frankel defect and Schottky defect. Silver bromide. Okay, so Schottky defect is shown by ionic substances in which the cations and anions are almost similar size, while the Frankel defects are shown by the while the Frankel defects are shown by the ionic solids, ionic crystal, in which there is a large difference between the cation and anion. Large difference in size between cation and anion. But Schottky defect is shown by the ions, by the ionic crystal in which cation and anions are similar size. So NaCl, KCl, cesium chloride, this ionic solids can show Schottky defect, while silver chloride, silver bromide, silver iodide, they can show Frankel defect. Okay, so these are mainly stoichiometric defect. Now see impurity defect. This is example of impurity defect. This is actually crystal lattice of sodium chloride. Crystal lattice of sodium chloride. You can see two sodium cations are missing from their own position, and at one side of sodium Na plus ion, one strontium 2 plus ion is present. From two side of the crystal, two Na plus are missing, and in one side of Na plus, one Sr2 plus ion is present. This Sr2 plus ion, that is strontium 2 plus ion, is impurity in the crystal of sodium chloride. So impurity defect: if molten NaCl containing a little amount of strontium chloride is crystallized, some of the side of Na plus are occupied by strontium 2 plus. If molten NaCl containing a little amount of strontium chloride is crystallized, some of the side of Na plus ion are occupied by strontium 2 plus. You can see from this figure 1.27. introduction of cation vacancy in NaCl by substitution of Na plus by strontium 2 plus. One Na plus ion is substituted by one Sr2 plus. Okay, and from the crystal lattice of NaCl, two Na plus are missing, because 2 Na plus ion means 2 positive charge, and instead of 2 Na plus ion, only one Sr2 plus ion is present in the crystal lattice, because one is strontium 2 plus ion charge is plus 2 and 2 Na plus total charge is plus 2, so charge is balanced, the crystal become electrically neutral. Okay, so if molten NaCl containing a little amount of Sr2 plus is crystallized, some of the site of Na plus ion are occupied by strontium 2 plus, and each strontium 2 plus replaces 2 Na plus ion. Each strontium 2 plus replaces 2 Na plus ion, and it occupies the site of one Na plus ion, and the other sites remain vacant. Okay, and the cationic vacancies thus produced are equal in number to that of strontium 2 plus ion. Another example of impurity defect is the solid solution of cadmium chloride and AgCl. Now see non-stoichiometric defect. Non-stoichiometric defect are those defects which alter or disturb the stoichiometry of the solid. Okay, and there are two type of non-stoichiometric solid. One is metal excess solid, another is metal deficiency solid. So metal excess solid, this is important, metal excess solid and metal excess defect and Frankel defect and Schottky defect. These three are mainly important defects. Okay, so metal excess defect, that is excess metal ion present, metal cation is present in the crystal lattice. Okay, if excess metal cation is present in the crystal lattice, then it is known as metal excess defect. Metal excess defect due to anionic vacancy. First see, metal excess defect due to anionic vacancy. Alkali halides like NaCl, KCl show this type of defect when crystal of NaCl are heated in an atmosphere of sodium vapor. When a crystal of sodium chloride are heated in presence of sodium vapor, the sodium atom from the sodium vapor are deposited on the surface of sodium chloride crystal. This is sodium chloride crystal, and above this sodium chloride crystal there are some sodium atom in the vapor state. Okay, and this sodium vapor deposited on the surface of sodium chloride crystal when sodium chloride is heated. The sodium atoms are deposited on the surface of crystal, and the Cl minus ion from the crystal, sodium chloride crystal, Cl minus ion diffuse to the surface of Cl minus ion from the sodium chloride crystal, diffuse to the surface of crystal and combine with this one Cl minus ion from this from the bulk of the sodium chloride crystal, diffused to the surface of sodium chloride crystal and combine with this Na sodium atom and gives NaCl. Okay, so the Cl minus ion diffuse to the surface of the crystal and combine with sodium atom to give NaCl, and this happens by loss of electron by sodium atom to form sodium ion, and the released electron diffuse into the crystal and occupy anionic site. Okay, as a result, crystal now has an excess sodium cation, and the anionic site occupied by unpaired electron are called F center. This type electron is diffused from the one Cl minus ion is diffused from this center, and the sodium atom which loses one electron, and this electron is present in the anionic site, anionic vacancy. Okay, and this site is known as F center. The anionic site occupied by unpaired electron are called F center. F center means Farbe center, that means color center. Due to the presence of this F center, the sodium chloride crystal impart yellow color. Okay, so this F center impart yellow color to the crystal of sodium chloride, and the color result by the excitation of these electrons when they absorb energy from the visible light falling on the crystal. Similarly, excess lithium makes lithium chloride crystal pink. Excess potassium makes potassium chloride crystal that is KCl crystal violet. Okay, so question is, why sodium chloride crystal become yellow when it is heated in presence of sodium vapor? Or similar question, why lithium chloride crystal become pink when it is heated in presence of lithium vapor? Similar question, why potassium chloride, that is KCl crystal, becomes violet when it is heated in presence of potassium vapor? And these all the three types of uh, defects are similar. Okay, these are metal excess defect. One more metal excess defect is given, it is also important. Zinc oxide metal excess defect due to presence of extra cation at the interstitial site. Okay, so when zinc oxide is heated, it becomes yellow. Zinc oxide is white in color at room temperature. On heating, it loses oxygen and it turns yellow color. So zinc oxide, when it heated, it forms Zn2 plus ion and 2 electrons, and the oxygen gas produced will release will leave the crystal lattice. Okay, so now there is an excess Zn zinc 2 plus ion in the crystal, and the formula of crystal becomes Zn1, and the formula become Zn1 plus XO, because one extra Zn2 plus is there in the one extra Zn2 plus ion is present in the crystal, in the interstitial site of crystal. The excess Zn2 plus ion move to the interstitial site and electrons to the neighboring interstitial site. Okay, and last type of defect, last defect, non-stoichiometric defect, is metal deficiency defect. Metal deficiency defect, there are many solids which are difficult to compare in stoichiometric composition, which are difficult to prepare in the stoichiometric composition and contain less amount of metal as compared to stoichiometric proportion. Example of metal deficiency defect: FeO, which is mostly found in found with a composition of Fe 0.95O, and it may actually range from Fe 0.930 to Fe 0.960. And in crystal of FeO, some Fe2 plus cation are missing, and loss of positive charge is made up by the presence of required number of Fe3 plus ions. Now see electrical property of crystalline solids. Electrical property of solids. Solids are three types based on electrical property. One type of conductors, semiconductors, and insulator. Conductors, the solids with the conductivity range between 10 to the 4 to 10 to the 7 ohm inverse meter inverse are called conductor. The solids with conductivity ranging between 10 to the 4 to 10 to the 7 ohm inverse meter inverse are called conductor. Metals have conductivity in the range of 10 to the 7. They are good conductor due to presence of free unpaired electrons. And insulators, these are solids solid with very low conductivities ranging between 10 to the minus 20 to 10 to the minus 10 ohm inverse meter inverse. And semiconductor, These are the solids with conductivity in the intermediate range from 10 to the power minus 6 to 10 to the power plus 4. Semiconductor, these are solids with conductivities in this intermediate range from 10 to the power minus 6 to 10 to the power plus 4 ohm. And in this chapter, semiconductor is important. Okay. Now, electrical property or conduction of electricity in metal. This is electrical property of solid. Okay, and there are three types of solid based on their conductivities: conductors, insulator, and semiconductor. Semiconductor is important, and according to band theory, any substance has two type of band. One is valence band, another is conduction band. Okay, this is valence band, and this is conduction band. In every substances there is a valence band, another is conduction band, and electrons are present in the valence band and conduction bands are empty generally. And according to band theory, the valence band and conduction band overlapping each other in metals. In conductor metal conductor, the valence band and conduction band overlap, and that's why they are good conductor of electricity. But in case of insulator, there is a large difference, large in a forbidden zones, energy gap between valence band, valence band are filled by electrons, remember that, and conduction band which is empty band. And in case of semiconductor, there is a small difference between the valence band and conduction band, in a small energy difference. That's why the conductivity of semiconductor is lower than conductivity of conductor. In metal conductor, the difference between the energy gap between in metal conductor, the valence band and conduction band overlapping each other, but in semiconductor, the valence band and conduction band, there is a small energy difference, energy gap. Okay. Now see some example of semiconductor, pure semiconductor, which are also called intrinsic semiconductor. These are silicon, germanium, Ge, etc. Silicon, germanium, Ge. These are some example of intrinsic semiconductor or pure semiconductor. But conductivity of pure semiconductor is very low. Conductivity of pure intrinsic semiconductor are very low. Okay, the conductivity of this intrinsic semiconductor is too low to be practical use, and their conductivity is increased by adding the conductivity of semiconductor is increased by adding an appropriate amount of suitable impurities, and this process is called, the addition of impurity in pure semiconductor is known as, this process is known as doping. So by doping, you can increase the conductivity of a semiconductor. Okay, so impure semiconductor are two types. One is electron rich semiconductor, that is also called n-type semiconductor. Okay, n-type. Impure semiconductor are two type. There one is n-type semiconductor, another is p-type semiconductor. N-type and pure p-type. Okay, silicon, germanium, these are pure semiconductor or intrinsic semiconductor. Okay, and from this pure semiconductor you can make extrinsic, that is impure semiconductor, by doping. So how n-type semiconductors or p-type semiconductors are formed? So n-type semiconductors are generally pure silicon, germanium, that is these are group 14 element. Pure semiconductor, that is silicon, germanium, these are group 14 element. And if you dope pure semiconductor, that is silicon, germanium, with group 15 element, like phosphorus, arsenic with group 15 element. You know, group 15 element has 5 valence electron. Then you will get n type semiconductor. N type means, n means negative, negative means electrons. In n type semiconductor there will be an extra free electrons. Okay, and when pure silicon or germanium are doping with group 15 element, that is silicon, phosphorus, then you will get n type semiconductor. But when you dope pure silicon or germanium with group 13 element like boron, okay, boron, gallium, then you will get electron deficient semiconductor, that is p type semiconductor. And in p type semiconductor there will be a electron hole. Okay, a positively charged electron hole. That's why this type of semiconductor is known as p type semiconductor. And p type semiconductor is formed after doping pure silicon or germanium with group 13 elements. Okay, silicon germanium can also be doped with a group 13 element, that is boron, aluminum, gallium. Okay, and after doping silicon germanium with group 13 element, we will get a p type semiconductor. P means positive. Positive means there in p type semiconductor there are some positively charged hole. Okay, and due to presence of positively charged hole in p type semiconductor and in n type semiconductor, due to presence of free electron, the conductivity of this n type p type semiconductor is higher than pure semiconductor. Okay, here application of semiconductor is given. And last, magnetic properties of solid. Okay, magnetic nature. Here some definition you have to read. On the basis of magnetic properties, some substances can be classified into 5 categories. Paramagnetic, like substances based on electrical properties, substances are 3 types: conductor, semiconductor, and insulator. Similarly, based on magnetic property, substances are paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, and ferrymagnetic. All these differences, all these terms you have to remember, important term. Okay, so first, paramagnetic substances. Paramagnetic substances are weakly attracted by magnetic field. Are weakly attracted by magnetic field, and they are mm, magnetized in magnetic field in the same direction, and they lose their magnetism in absence of magnetic field. And paramagnetism is due to the presence of one or more unpaired electron, okay, which are attracted by the magnetic field. Example of paramagnetic substances: Cu2 plus, Fe3 plus, Cr3 plus. These are paramagnetic substances which are weakly attracted by magnetic field, and paramagnetism is due to presence of one or more unpaired electrons. So definition with example you have to remember. Definition of paramagnetism or paramagnetic substance. So substances those are weakly attracted by magnetic field, they are known as paramagnetic substances. Now second, diamagnetic. These are weakly repelled, these are not attracted. Diamagnetic substances, that is diamagnetism. Diamagnetic substances are weakly repelled by magnetic field. Example of diamagnetic substances: water, NaCl, benzene, C6H6. Some example of diamagnetic substances. And they are weakly magnetized in magnetic field in opposite direction. Diamagnetism is shown by those substances in which all electrons are paired. If in a substance all electrons are paired, then the substance will show diamagnetism. Okay, so diamagnetism is shown by those substances in which all the electrons are paired and there are no unpaired electrons. Next type of substance, ferromagnetism. Important term, ferromagnetism. This like paramagnetism. Okay, few substances like iron, cobalt, nickel. Few substances like iron, cobalt, nickel Okay, these substances are very strongly attracted by magnetic field. Few substances like iron, cobalt, nickel, these are very strongly attracted by magnetic field, and such substances are called ferromagnetic substances. Okay, so ferromagnetic substances are very strongly attracted by magnetic field. Example of ferromagnetic substances are iron, cobalt, nickel, etc. Okay. And in ferromagnetic substance there are large number of unpaired electron, and all unpaired electron are oriented in same direction. Okay, and one thing you have to remember, that the magnetism is arise due to presence of unpaired electron. And in ferromagnetic substances, you can see in ferromagnetic substances all there are large number of unpaired electron, and all the unpaired electrons are oriented in the same direction. Now see anti-ferromagnetic substance. And one more thing, ferromagnetic substances can be used to make permanent magnet. Okay, so ferromagnetic substances become a permanent magnet. You can make permanent magnet using ferromagnetic substance like iron, nickel, cobalt. Next, anti-ferromagnetic substance. This is like diamagnetism. Substances like manganese oxide, MnO, manganese oxide, showing anti-ferromagnetism. They have domain structure similar to ferromagnetic substance, but their domain are oppositely oriented and cancel out each other magnetic moment. In antiferromagnetic substances, there are also many unpaired electrons are present, but the unpaired electrons are in opposite direction. Here you can see in B, it is given 1, 2, 3 unpaired electron in upward direction. Okay, and 3 unpaired electron in downward direction. So their magnetic moment cancel each other. So their magnetic moment becomes 0. That's why they are called antiferromagnetic substances. And ferrimagnetic, last one is ferrimagnetic substances or ferrimagnetism. Ferrimagnetism is observed when the magnetic moment of the domain means each unpaired electron is here assumed as domain. Okay, so in ferrimagnetism is observed when magnetic moment of the domain in the substance are aligned in parallel and anti-parallel direction in unequal number, not in equal number. It is equal number in antiferromagnetic substance, but in ferrimagnetism, the magnetic moment of the domains in the substance are aligned in parallel and antiparallel direction in unequal number, and they are weakly attracted by magnetic field. Ferrimagnetic substance like paramagnetic substance, they are weakly attracted by magnetic field. Okay, an example of ferrimagnetic substance, magnetite Fe3O4, ferrites Mg Fe2O4, and Zn Fe2O4. These are some example of ferrimagnetic substance. And these ferrimagnetic substances also lose ferrimagnetism on heating and become paramagnetic. Okay, so in ferrimagnetic substance also there are large number of unpaired electron, but in an unequal number. Some, see, total 1 2 3 4 4 unpaired electrons are in upward direction and 2 unpaired electron in downward direction. Okay, so these 5 definition with example you have to remember. 5 type of magnetic substances, that is paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic and ferrimagnetic. Okay, bye students.